What if time had no beginning? What if everything you've ever known, space, matter, reality itself, emerged not from something, but from absolutely nothing? Tonight, we drift into the void before time. Not science fiction, but real theories that stretch the boundaries of cosmology and consciousness. Was there a before, or did time itself spark into existence with the Big Bang? Let your eyes grow heavy as we journey to where logic collapses and the universe hasn't even begun. This is Echoes from Tomorrow, and you're listening to Before the Big Bang. Was there something or nothing? Chapter 1. The problem with before. Imagine you're sailing toward the North Pole. With every step, the compass shifts. Eventually, every direction becomes south. There is no such thing as north of the North Pole. It simply doesn't exist within the framework we're using. Now, apply that idea to the universe, to time itself. What if asking what came before the Big Bang is like asking, what's north of the North Pole? It feels like a valid question, instinctive, even, but it may not actually make sense. Because time and space, as we understand them, are not standalone entities. They're not separate ingredients in a cosmic recipe. They are intertwined part of a single, unified fabric known as space-time. This concept lies at the heart of Einstein's general theory of relativity. Space and time curve, stretch, and bend together. You cannot change one without affecting the other. And according to our current understanding, this space-time fabric came into existence with the Big Bang. There was no stage upon which the Big Bang occurred. No space to expand into. No time ticking in the background. Time didn't exist and then start ticking once the fireworks began. Instead, time itself may have been born in that moment, an integral part of the unfolding cosmos. So when we ask, what happened before the Big Bang? We're doing something interesting. We're applying human intuition, rooted in cause and effect, to a realm where those ideas might not even apply. Every second of our lives is built on a sequence. One moment follows the next. One event causes another. But what if that structure, the flow of time, isn't universal? What if it's a product of the universe rather than a condition that existed before it? To explore this, physicists have turned to the mathematics of relativity and the strange terrain of quantum mechanics, and what they find is both beautiful and unsettling. In relativity, space-time behaves like a smooth surface. It can bend, curve, ripple. But just as you can't have a wave without a sea, you can't have motion or events without time. If time doesn't exist, then neither does the concept of before. That might seem like a clever word trick, but it has real implications. It means that the question itself, what came before the Big Bang, might be fundamentally flawed, not because we haven't found the answer, but because there may be no answer to find. Still, we are humans. Our minds crave beginnings. We want a cause, a source, a reason. Saying there was no before feels unsatisfying, and that discomfort fuels further inquiry. What does it mean to say time began? Was there a boundary? A wall we can't see past? Or was the beginning more like a transition, a phase change in the structure of reality? Some scientists suggest we think of the early universe not as a point in time, but as a shift in states, like water freezing into ice or steam condensing into droplets. A change in the conditions of existence itself. In this analogy, time might have been a latent property, something that emerged when the universe crossed a threshold. And prior to that moment, the universe existed in a different, timeless form, not in a void, not in darkness, but in a state that defies our current frameworks. This brings us into the domain of quantum cosmology, where things get even stranger. At quantum scales, the rules of classical physics dissolve. Time becomes fuzzy. Events don't occur in neat sequences. Instead, possibilities overlap. Probabilities rule. And nothing is definite until it's observed. In some interpretations of quantum theory, the very act of measurement or awareness affects the system. So what happens when we apply quantum principles to the entire universe? Can we observe the beginning without being outside of it? Can we measure the creation of time without already existing in time? These aren't just poetic puzzles. They're deep scientific problems with real mathematical frameworks behind them. The wave function of the universe is a term used in quantum cosmology. It tries to describe the probability, distribution of all possible states the universe could be in. But even this tool runs into difficulties when time itself is uncertain. Some physicists have proposed a timeless version of this wave function, a model in which the universe simply is a static entity, unchanging in the deepest sense, but experienced by conscious beings, like us, as if it's unfolding in time, like flipping through the pages are all there. The movement is an illusion born from perspective. In this view, the flow of time is a trick of consciousness, a byproduct of how we process information. And the Big Bang wasn't the start of time, but merely the first page we can read. Others propose that the Big Bang was not a beginning, but a boundary, a place where our current laws of physics break down, a veil beyond which we cannot yet see, not because it's forbidden, but because we lack the tools. Still, these models don't all agree. Some suggest a singularity, an infinitely dense point where all of space-time compresses. Others argue that the singularity is a mathematical artifact, not a physical reality, a signal that our theories, like old maps, reach their edge. The further back we go, the more blurred the picture becomes. Yet one thing is clear: time, as we experience it, is not fundamental. It may be emergent, conditional, fragile, a product of entropy, memory, perception. It may not have existed in the same form at the dawn of the universe. And that changes everything. When we ask what came before, we're assuming that time stretches infinitely backward. But maybe it doesn't. Maybe time has a starting point, not in the sense of a spark lighting a fuse, but in the sense of a concept being born. So here we are, inside this concept, living in time, bound by cause and effect, measuring the seconds as they slip past. But the moment we try to look beyond the first tick of the cosmic clock, we find ourselves staring into something timeless, a domain where before has no meaning, no direction, no foothold. Just as there is no north of the North Pole, there may be no before the beginning. And yet, for some reason, we can still imagine it. That, in itself, might be the greatest mystery of all. Chapter 2: Hawking's No Boundary Universe. Picture a globe in your mind. You can walk around it endlessly, but you'll never find an edge. There's no cliff where the planet ends, no sudden drop. If you trace the equator, you're not reaching a starting line. You're simply following a path that loops without boundary. Now imagine applying that same idea to the universe itself. That's what physicist Stephen Hawking proposed. A universe that is finite, but has no edge. a cosmos without a starting point. Not because it goes on forever, but because the concept of a beginning loses meaning when you're dealing with curved space-time. Hawking, working with James Hart, introduced a model called the No Boundary proposal. It's one of the most striking and elegant ideas in modern cosmology. In this model, the universe isn't infinite, but it also doesn't have a boundary where it all began. Instead, time itself transforms in the earliest moments of the cosmos, right at the so-called beginning. What we usually refer to as the Big Bang, something strange happens. Time doesn't abruptly start ticking. It doesn't explode out of a void. Instead, it undergoes a transformation. It becomes imaginary. Not imaginary as in made up or fictional, but imaginary in the mathematical sense, like the square root of -1. This idea comes from the realm of quantum mechanics and complex numbers. When time becomes imaginary, it behaves more like a dimension of space than something that flows. It smooths out the sharp point we imagine as the beginning of everything. Think of a cone. The sharp tip is the Big Bang in classical terms. But in Hawking's model, that tip gets rounded off. There's no singular point where everything starts. Instead, the early universe looks more like a sphere, curving gently, without a jagged edge or a clear origin. The geometry becomes smooth, continuous, boundaryless. Implications of this are profound. It suggests that the universe didn't begin in a flash from nothing. It didn't emerge from a singularity with infinite density. Rather, it gradually transitioned from a timeless, space-like state into the time-filled cosmos we know today. Before that transition, time simply didn't exist as we understand it. There was no before the Big Bang because time itself was in a different form, a geometric property, not a ticking clock. So when we talk about the creation of the universe, we may be misled by our own language. Words like before, beginning, and start carry assumptions based on how we experience time in everyday life. But in the realm of quantum gravity and curved space-time, these concepts break down. Hawking's model invites us to imagine a universe that is self-contained, one that doesn't require something outside of it to set it in motion. No external time, no divine spark, no edge from which it emerged. It just is. That may sound unsettling or oddly peaceful. A universe that simply exists, finite yet without edges, real yet In this view, asking what caused the universe becomes like asking what's outside the surface of a sphere. The question makes sense in everyday experience, but in this context, it may have no answer, not because we haven't found it, but because it doesn't need one. Critics have debated the No Boundary proposal for decades. Some argue it relies too heavily on speculative mathematics. Others point out that imaginary time, while useful in calculations, may not correspond to physical reality. But even among skeptics, the idea is respected for its creativity and boldness. It shifts the frame. Instead of trying to peer behind a cosmic curtain, it invites us to rethink the shape of the curtain itself. In Hawking's model, the laws of quantum mechanics and general relativity work together. The early universe behaves like a quantum object, described not by fixed histories but by probabilities. In this haze of potential realities, the most likely one is the one that looks smooth and bound. That's the universe we inhabit. Or at least, that's the hypothesis. In practical terms, this model could help explain why the universe appears so uniform in all directions. It provides a natural reason for the absence of irregularities at the largest scales. It also avoids the problem of a singularity, where density and temperature go to infinity and physics breaks down. Instead of hitting a wall in our equations, the math glides gently around the early moments, just like a traveler circling a globe. This doesn't mean the no-boundary model is proven. It remains one of several competing ideas in cosmology. Other models propose bouncing universes, hidden dimensions, or multiverse landscapes. But what makes Hawking's vision so compelling is its simplicity. No exotic ingredients. No need for a trigger outside time. Just a reshaping of how we think about beginnings. And perhaps most striking of all is the emotional shift it invites. We often imagine the birth of the universe as a violent eruption, a cosmic bang breaking the silence. But in the no-boundary model, creation is smooth, quiet, inevitable, less like a bomb, more like a sunrise. There was no explosion, no chaos. Just the gentle unfolding of geometry, a transformation from timelessness to time, from a realm where space and time are indistinguishable, to one where seconds pass and galaxies form. That's the universe we know. But its origins may lie in a place where origin itself has no meaning. The no-boundary universe asks us to surrender our craving for edges. 4 starts, 4 explanations rooted in linear time. It invites us to consider that the universe didn't begin in any conventional sense. It simply came to be not from a place, not from a moment, but from a mathematical truth embedded in the structure of reality. And if that's true, then perhaps the most mysterious thing about the universe isn't how it began, but how our minds evolved to wonder about beginnings at all. Chapter 3. Cyclic Universe Theories. What if this isn't the first time? What if the universe we live in is just one of many iterations, an echo in a repeating pattern that stretches back beyond memory and forward, beyond imagination? Some physicists believe the universe doesn't have a singular beginning or end. Instead, it may be part of a grand cycle, expanding and contracting endlessly, like the rise and fall of a cosmic breath. This is the idea behind cyclic universe theories. In these models, the Big Bang wasn't the ultimate origin. It was just the latest in a series of events that occur over incomprehensibly long times. Picture the universe like a beating heart. It expands outward, cools, forms galaxies and stars, life and time. Then, after trillions of years, gravity slowly pulls everything back together. Matter collapses inward. The universe contracts. Heat and density rise again, and eventually it reaches a critical point, a bounce, where a new expansion begins. Another Big Bang, another cycle, another universe, born from the ashes of the last. In this framework, our universe is one frame in an eternal movie, and every version might be slightly different, laws of physics tweaked, structures rearranged, timelines shifted. It's a compelling vision, one that avoids the discomfort of a true beginning. It removes the need for something to emerge from nothing. Instead of asking, what caused the universe? We ask, what cycle are we in now? Some ancient traditions imagined the cosmos this way long before physics existed. Hindu cosmology, for example, speaks of vast cycles of creation and destruction, each spanning billions of years. But in modern science, the idea gained traction as an answer to problems with the standard Big Bang model, like the singularity, an infinite point of density where our laws of physics break down. In a cyclic model, There is no singularity. The universe never compresses into an absolute point. Instead, the collapse slows and rebounds before that happens. One version of the cyclic idea is the ekpyrotic universe. Proposed in the early 2000s, this theory suggests that our universe is a brain floating in a higher dimensional space. Occasionally, it collides with another brain, triggering a burst of energy, a big bang from which a new cycle begins. Another version, based on loop quantum cosmology, uses principles from quantum gravity to propose that space-time is discrete, not continuous. In this view, the universe can only shrink to a certain minimum size before quantum effects cause it to bounce back outward. Each of these models seeks to do something profound, to eliminate the need for a beginning, to replace the concept of origin with one of rhythm, and if the universe has no beginning, it might also have no end. Just an infinite pulse, expansion, contraction, rebirth over and over. But these ideas are not without challenges. For one, entropy, the gradual loss of usable energy over time, seems to resist this kind of recycling. Each cycle should be messier than the last, more disordered. So how can a new universe be born fresh from the ruins of the old? Some models address this by suggesting that each bounce wipes the slate clean. Others propose mechanisms for resetting entropy or embedding it in hidden dimensions. It's speculative, but so is all of cosmology at this scale. What's intriguing is that new data from cosmic microwave, background radiation, and gravitational waves may one day support or rule out these models. Even now, subtle patterns in the oldest light in the universe are being studied for signs of prior cycles, echoes, perhaps of earlier expansions. If we ever detect such a signature, it would be one of the most transformative discoveries in history. It would mean that everything we know, every star, every atom, every human thought is part of an eternal process, and the universe we observe is just one stanza in an infinite poem. But what would that mean for us? If the universe resets forever, does anything last? Does anything matter? In a strange way, the answer might be more comforting than unsettling. In a cyclic cosmos, nothing is ever truly lost. Every collapse leads to renewal. Every ending is a prelude. And perhaps, in some deep and unreachable way, every version of the universe carries traces of the ones before it, like memories buried in the structure of space itself. Some physicists even suggest that this process is necessary for life to exist at all. Maybe only in certain cycles do conditions align perfectly for complexity to arise for galaxies, planets, consciousness. If that's true, then the fact that we're here, thinking about the universe, could be the result of countless cycles that came before each one, preparing the stage for this one. That idea reframes everything. We are not accidents of a single explosion, but products of a long cosmic rhythm. Our existence, fleeting as it seems, is woven into a pattern that transcends time. And while we may never witness the next bounce, or remember the last one, we are part of the cycle, nonetheless. So what version of reality are we in now? The first, the thousandth, the millionth? No one knows. And maybe it doesn't matter. What matters is that we're here, in this moment, in this cycle, asking questions that echo beyond the edge of time. Chapter 4: Quantum Foam and the Vacuum That Isn't Empty. In quantum mechanics, even nothing isn't truly nothing. What we think of as empty space is anything but empty. on the smallest scales, far beneath atoms, beneath protons. Even beneath quarks, space is alive with restless energy. This ever-present turbulence is known as quantum foam. It's not a poetic phrase. It's a real phenomenon, a term coined by physicist John Wheeler to describe the jittery, chaotic nature of space-time at the Planck scale. At this level, space itself is no longer smooth. It bubbles, trembles, fluctuates. Virtual particles appear and disappear within fractions of a second, borrowing energy from the vacuum and giving it back just as quickly. These particles can't be seen directly, but their effects are measurable. They leave fingerprints on experiments. They shift the energy levels of atoms. They even influence how light behaves as it passes through a vacuum. It's as if the universe has a heartbeat at its most fundamental level, a constant flickering of possibility, and it's here, in this roiling sea of uncertainty, that some physicists believe the universe itself may have been born. According to one leading idea, the entire cosmos may have sprung from a single fluctuation in this quantum vacuum, a tiny patch of space-time a mere speck could have, by random chance, reached a critical threshold, a momentary imbalance, a ripple that didn't cancel itself out. Instead, it grew, rapidly, violently, exponentially. That's inflation theory, a model proposing that the early universe expanded at an extraordinary rate, driven by vacuum energy. And what triggered that expansion? Perhaps it was a fluctuation in the quantum foam. Just a random event in a sea of random events. But this one didn't vanish. It became space. It became time. It became everything. In this view, the Big Bang wasn't an explosion in space, it was an expansion of space, initiated by the energetic structure of the vacuum. Before that, there may have been no before in the classical sense, but there was the quantum foam, a field of potential, seething with virtual particles and temporary states. Some call it nothing, others call it the source of all. It's strange to think that what we perceive as empty is actually full of energy, full of motion, full of fleeting realities that almost exist. And from this sea of uncertainty, one fluctuation may have won the cosmic lottery, creating a region of expanding space-time, our universe. The beauty of this theory is that it doesn't require a cause in the traditional sense. No external hand, no prime mover. Just physics doing what physics does. The rules of quantum mechanics, applied to nothing, may produce something. The universe as a quantum accident, a spark in the dark. Of course, this raises deep questions. If one fluctuation can become a universe, why not more? And if the quantum vacuum is still bubbling today, could new universes still be forming, invisible to us? Some cosmologists think so. The concept of a multiverse emerges naturally from this framework. If space can expand from a fluctuation once, it could do so again and again forever. Each new universe would bud off like a bubble, separated from the others by vast, unreachable distances. Ours is just one in a growing foam of realities. But even if we focus only on this universe, the implications of quantum foam are profound. It suggests that the universe doesn't rest on nothing, it floats on uncertainty. That even the most stable vacuum is, underneath, a storm of activity. In some models, vacuum energy has structured fields that can settle into different states. Much like water can be liquid or ice or steam, our universe may represent one such stable state. Before it settled, the vacuum may have had more energy enough to drive the inflationary expansion. Once expansion cooled and the energy dropped, matter could condense, galaxies could form, stars could shine. But it all began with a quantum fluctuation, a brief, silent shift in the vacuum's balance. No explosion, no bang, just an emergence. This idea doesn't answer every question. It doesn't tell us why the laws of physics are the way they are, or why this particular fluctuation gave rise to a universe with stars and life. But it offers a mechanism, a framework grounded in what we know about how particles behave at the smallest scales. Some critics argue that quantum foam is still a speculative concept, that we haven't directly observed it. That's true, but its effects are supported by experiments. The Casimir effect, for example, demonstrates how virtual particles can exert pressure on objects, even in a vacuum. Particle and antiparticle pairs flicker into existence and vanish constantly in high-energy fields. The vacuum is not passive. It has rules. It has structure. It responds. So the idea that it could also give rise to space-time itself isn't as far-fetched as it might seem. In a strange twist, nothing may be the most fertile thing of all. If you wait long enough in a field of quantum foam, something might appear, not because it's destined, but because, in a world of infinite possibilities, even the rarest events eventually happen, including, perhaps, the birth of a universe. Ours. This theory reframes the mystery. Instead of asking how something came from nothing, we begin to question what nothing really means. Maybe nothing is unstable. Maybe nothing contains the seeds of everything. Maybe the deepest truth is that the void isn't void at all. It's alive, unpredictable, creative, and somewhere, in that sea of quantum uncertainty, a ripple became real. A hiccup turned into expansion. A fluctuation unfolded into stars. From that, everything. Chapter 5. The Multiverse Landscape. What if our universe is just a drop in an ocean? For centuries, we believed the cosmos was everything there is, one universe, vast and singular, containing all matter, space, and time. But modern physics is beginning to suggest something far more complex and unsettling. According to string theory and other advanced models of reality, the universe we know may be only one bubble in a vast multiverse, a landscape of countless possible universes, each with its own version of physical laws, particles, and dimensions. This idea doesn't come from science fiction. It emerges naturally from two powerful theories: string theory and eternal inflation. String theory, in its most ambitious form, tries to unify all the forces of nature by modeling particles not as points, but as tiny, vibrating strings. These strings can vibrate in different modes, giving rise to different particles. But the theory only works consistently in high space, usually 10 or 11 dimensions, depending on the version. And here's where things get strange. To make string theory compatible with our observable universe, many of these extra dimensions must be curled up or compactified in very specific ways. The number of ways to do that? Nearly infinite. Each configuration creates a different vacuum state, a different version of physics, one with a different speed of light, different charges, different masses, different forces. This enormous set of possibilities is called the string theory landscape. It may contain 10 to the power of 500 different solutions, each one a potential universe with its own rules. But how do we get from theory to reality? That's where eternal inflation comes in. Inflation is the theory that in the earliest fraction of a second after the Big Bang, our universe underwent a period of exponential expansion. Space itself grew faster than the speed of light, smoothing out the cosmos and laying the foundation for everything we see today. Eternal inflation takes that concept a step further. It proposes that inflation never completely stops. In most regions of space, the inflationary process continues endlessly, creating a kind of cosmic foam where tiny patches occasionally stop inflating and form pocket universes like bubbles in boiling water. Our universe would be one of those bubbles. Others continue to form forever, each with different properties, depending on how the vacuum energy settles in that region. Combined with the string landscape, this suggests a multiverse filled with universes, each one a bubble with unique laws of nature, separated by inflating space that prevents them from ever interacting. If this is true, the Big Bang wasn't the beginning of everything. It was the beginning of our particular bubble, the real beginning, the start of the inflationary process. The origin of the landscape may lie beyond our reach, outside the boundaries of our physics, perhaps even outside the limits of human comprehension. The implications are vast. In a multiverse, everything that can happen does happen somewhere. There may be universes where stars never formed, where gravity is stronger or weaker, where light moves differently, where time flows in unexpected ways. There may even be versions where intelligent life evolved under conditions completely alien to ours. The multiverse raises philosophical and scientific questions that shake the foundations of what we consider reality. If countless versions of the universe exist, what makes ours special? Is it a random accident that we're in a universe with the right conditions for life? Or is there a deeper reason? Some scientists turn to the anthropic principle for an answer. It says we observe this universe because it's the one compatible with our existence. In universes with different laws, observers like us might never emerge, so we wouldn't be there to ask questions. It's not a satisfying answer for everyone. It feels circular, almost evasive, but it might be the best we can do given our limited perspective inside one bubble. Others hope that the multiverse is testable, that future experiments or observations might detect signatures of other universes, such as collisions between bubbles or patterns in the cosmic microwave background. So far, evidence is inconclusive, but the theories remain compelling because they provide a natural framework for understanding the strange fine-tuning of our universe. Why does gravity have exactly the strength it does? Why are the constants of nature balanced so delicately that atoms can form, stars can shine, and life can emerge? In a single universe model, these values seem suspiciously perfect. In a multiverse, they're just one outcome among many. We got lucky. Or rather, we landed in a universe where life is possible, and so we're here to notice. Of course, not everyone agrees. Some physicists argue that the multiverse is unscientific because it may be fundamentally untestable. If we can never interact with or observe these other universes, how can we know they exist? Is it science or metaphysics? That debate continues, but even critics admit that the multiverse is a natural consequence of theories that work well in other areas. If those theories are correct, the multiverse may come along for the ride whether we like it or not. Still, the idea is deeply humbling. It suggests that our entire observable universe, everything we've ever seen through telescopes, every galaxy, every star, every planet is just one tiny region in a vast, unobservably expanse, a drop in an endless ocean, and the ocean is still growing. In this view, the real mystery isn't how our universe began, but why it took this particular form. Why, out of the vast landscape of possibilities, we find ourselves in a world that feels so precisely tuned for our existence. Was it chance, necessity, or something beyond our grasp entirely? The multiverse doesn't give us clear answers, but it expands the stage on which the drama of existence unfolds. It challenges us to look beyond what we can see and consider that the reality we know is only a fraction of what is, that behind the cosmic curtain lies a wilderness of worlds unreachable, unknowable, and yet possibly real. And if that's true, then our journey to understand the universe is only just beginning. Chapter 6. The final question. Why is there something rather than nothing? Even if we one day understand how the universe began, how space-time emerged, how particles formed and galaxies evolved, there remains one question that sits silently at the edge of all answers. Why is there something rather than nothing? It's not a scientific question in the traditional sense. It doesn't point to a specific equation or observable phenomenon. It's more like a mirror held up to existence itself, asking the most fundamental question we can form. Why does anything exist at all? Why is there a universe instead of an infinite void where nothing ever happened, where time never ticked, where not even the concept of emptiness made sense? This question has haunted thinkers for centuries, philosophers, theologians, scientists, poets. It reaches deeper than the Big Bang, deeper than quantum fields or It asks not about mechanisms, but meaning. Some suggest the answer is chance, that existence is a fluke, a random event with no cause, no reason, no purpose. In a sea of infinite possibilities, even something as improbable as a universe must eventually occur. In this view, the universe is a cosmic accident, unexpected, unplanned, but ultimately real. Others argue its necessity, that reality must exist because non-existence is unstable or impossible. If the laws of logic or mathematics are somehow built into the fabric of reality, then perhaps existence is inevitable. In this framework, nothing isn't a true state, it's merely the absence of something. And once even the tiniest fluctuation appears, it becomes everything. There are also those who invoke a creator, a conscious mind, a timeless intelligence, a being outside space and time who chose to bring the universe into being. This is the domain of theology and metaphysics, not physics, but it represents a serious attempt to answer the unanswerable. If everything we see had a cause, they reason, then perhaps the universe itself must also have one an uncaused cause. But each of these answers leads to more questions. If it's chance, then why this universe, with these laws, capable of supporting life? If it's necessity, what enforces that necessity? If it's design, who or what is the designer, and where did they come from? The trail never quite ends. It loops back into itself, into a fog where logic begins to dissolve. The problem with nothing is that we can't truly imagine it. When we say nothing, we often picture empty space. But space is something, a structure that can bend, warp, expand. When we say nothing, we might imagine darkness. But darkness is the absence of light in space. Still something. True nothingness means no space, number time, no energy, no laws, no consciousness, no possibility, no existence. And yet here we are, thinking about it. asking questions inside a reality filled with stars and atoms and breath. Some physicists try to build models of a universe from nothing. Quantum cosmology suggests that vacuum fluctuations or the collapse of a wave function might give rise to existence. But even these rely on something, on physical laws, on a quantum vacuum, on a set of rules that allows something to emerge. So again we ask, why are those rules there at all? Why is there a logic to the universe? Why not chaos, or better yet, nothing? Perhaps the question is unanswerable not because it's too hard, but because it's rooted in the limits of human thought. We are beings evolved to navigate space and time, to recognize patterns, to seek causes. Maybe our brains are simply not built to comprehend non-existence. Maybe we're trying to apply language and logic to something beyond their reach. But maybe that's the point. Maybe the mystery is what makes existence beautiful. The very fact that we can ask this question, that we can wonder about our place in a universe that might not have had to be here at all, is extraordinary. It means that the universe is not only vast and complex, but also capable of producing creatures that reflect on its nature. Consciousness, curiosity, awe, these are not side effects. They are signs that existence is not meaningless, even if we can't explain it. In the quiet spaces between stars, the universe doesn't explain itself. It simply shines. It expands. It breathes. And we, small and fragile as we are, get to be part of that story. Maybe the final answer will never come. Maybe it will never be needed. Maybe the question itself is the final truth, that something exists, and we are here to witness it. In a cosmos that could have been nothing, that could have never happened at all. Here you are, listening, wondering, alive, and maybe that's enough. You've just journeyed into the unknown where time has no foothold, and answers dissolve into possibilities. Before the Big Bang, there may have been nothing, or an eternal cycle, or infinite universes waiting to be born. Maybe the universe didn't come from somewhere. Maybe it is the somewhere. And as you drift into sleep, remember, not every mystery was meant to be solved. Some are simply meant to be felt. This is Echoes from Tomorrow. Good night, traveler, and dream of the void before it all began.